Welcome, dynamics students. In this lecture we're going to be going over some actual calculations for polar moment of inertia and take a little bit of a look at products of inertia. To recap, these are super important because these are our characteristics of our rigid body that we're going to use to link angular momentum of that rigid body around any point to later use to relate to resultant or net applied moment to that body. So being able to calculate those properties of the body itself gives us something that we need to know to relate rotational acceleration basically to applied moment. So just a recap, our polar moment of inertia, otherwise known as I sub z, is the moment of that body about the z-axis, and of course the z-axis in all of our derivations and examples for this part of the course is the planar normal to the plane of motion that we're moving in. So we're dealing with rigid body planar motion. That plane is unless otherwise specified, is the xy plane, so the I sub z is the moment of inertia with respect to our planar normal. And by default, we're going to assume that it is an axis parallel to the planar normal, and it's through the point of interest, which we've been calling point P. So we get I subscript zp, and that's defined as the integral over the whole body's mass of the sum of the distance in the x direction to point P plus the distance in the y direction to point P. Again, integrated over the whole mass of the body. So let's get some practice just taking a look at one of these for something, a standard shape, something that we'll definitely encounter in rotational motion, a cylinder. And in this case, the cylinder is located with its axis parallel to the z-axis, so this would definitely be like a rotating shaft. So maybe we'd want to design a shaft and tailor its moment of inertia about the z-axis to give it more or less resistance to rotation. It would be something fairly typical. So we can use cylindrical coordinates to define our mass element. Always the important thing in these integrals is defining our volume element, mass element, area element, whatever. That is something that we can integrate and that we can relate to other things we want to know, like in this case, the distance from the axis in these two directions. So our mass element is going to be the density, and this could be constant for a uniform cylinder, or it could vary with position. And if it does, we'll have this just expressed as some function of r theta or z. And then we have r d theta dr dz, which is effectively the volume element for a cylinder. Okay, lucky for us, the more difficult parts of the integral are distance, in this case from the center of mass in the x direction, and distance from the center of mass in the y direction. If we square those both, we get r, which is perfect for cylindrical coordinates. So basically we have our mass element times r squared as the integrand, and then we're going to integrate theta all the way around the circle from 0 to 2 pi. We're going to integrate the radius from 0, which is on the z-axis, all the way out to the radius of the cylinder, r. And then we're going to integrate the length from negative L to L, the full length. And so if we execute that integral, we end up getting r squared times the mass over 2. So just to show how configuration really matters, let's take that same exact cylinder, same dimension, same mass distribution, and let's rotate it such that now, rather than having the z-axis be along the cylinder axis, it's at right angles. So now we have to be a little bit more creative in determining our expressions for distance of any mass bit from the z-axis, and we can still use our polar coordinate mass bit. So we're going to use our d theta dr dz, which we're gonna add up along the cylinder axis, but we need to multiply by y sub c squared plus x sub c squared. Well, x sub c is not a problem because we're going to end up integrating with respect to x. So what we really need is an expression for our y sub c, which is, of course, an essential part of our definition of our polar moment of inertia. We need a way to integrate y sub c with respect to something we intend to integrate with. So we need y sub c in terms of theta and r, which we can use some trig and get that. So r sine theta, where theta is defined as being an angle around defining that circle of the cylinder, and r is from the axis of the cylinder outwards. So any given y, if this is a cross-section of the cylinder, we have z, y, for any given angle theta, and r, our actual y position is just simply given by r sine theta. Makes it easy. So we can square that, and that's, of course, our y distance from the center of mass, which we're now assuming is the center of the cylinder. So we're actually getting kind of the y centroid. If the mass distribution doesn't put that at the center of mass, we will account for it here in our whatever that density function would be. We're assuming it's uniform for now. So we end up again with an r multiplier by everything, and this is now r times y squared plus x squared, with y squared being r squared sine theta squared. So we now have the integral of a sum, and we're just going to integrate that again all the way around theta from 0 to 2 pi, all the way out the radius from 0 to the radius of the cylinder, and then from end to end, this time in the x direction, because the cylinder is aligned along the x direction, so we go from x equals negative L over 2 to x equals L over 2. And so, of course, this first term is a constant with respect to x, but we'll end up integrating and getting a cubed term out of this one. So to do the integral, we can just walk through our basic rules of integration. In this case, we deployed a trig identity here to make the integration easier. The integral with respect to theta, that's sine squared, is much easier handled in its sine 2 theta term form, but otherwise we just integrate the continuous functions with respect to what we're integrating with. In this case, what we've done is we just integrated here with respect to theta. So now we have a theta term out here, and we're going to apply our limits of integration, and then take that term with the limits, and then integrate with respect to r and x, which are much simpler integrals. So this fell out of trig identities and some integration by parts, something that you can look up in an integral table as well. And keep going, just keep integrating again, with respect to each different term in order, inside to outside. So first with respect to r, and lastly with respect to the distance from the center of mass, x sub c, and putting in the final limits, we end up getting this term, which is much different than this term if that very same cylinder were oriented with its axis along the z-axis. So this is the polar moment of inertia for that same cylinder if it's located with its center of mass on the z-axis, but oriented, its own axis oriented perpendicular to the z-axis. So so we've still got an r squared term, like we did in the case where the cylinder was aligned with respect to the z-axis, but we've got a fairly significant amount that is now directly proportional to the cylinder length. We didn't have any dependence on the cylinder length up in this case because the length never varied. It was never a part of how the mass distribution varied around our z-axis. So those are two kind of simple examples of our polar moment of inertia, an integral calculation. So you can deploy those also for simple shapes, circles, cylinders, some types of rectangular sections. There are tables with moment of inertia. So you can just look these up if you don't want to have to do the integral, but be very careful. Make sure that you know what point they're being taken around. Is it with respect to the z-axis through the center of mass, or with respect to the z-axis on one side? Speaking of which, through the center of mass versus on one side, what if our point of interest wasn't at the center of mass? And we need a moment of inertia to do an angular momentum calculation. We can use the parallel axis theorem, which, and this is a review of that. I won't prove it, I'll just state it. Excuse me, but it's used to relate the moment of inertia of any kind of body around any point not at the center of mass to that same moment of inertia of that body at the center of mass. And this applies to the moment of inertia in any, along any axis, as well as the z-axis, which is that polar combination of x and y. So it basically says our moment of inertia about some other point is the moment of inertia around the axis that goes through the center of mass, plus the distance, the right angle distance from the point that you're talking about to the center of mass times the mass of the whole body. So this is, again, something that you've probably seen before in discussions of moment of inertia in statics or physics. So we're not going to prove it, but we're going to state it and then use it. Again, this is something very useful if you look up moments of inertia about the center of mass of a particular shape, maybe in a handbook, and you need to know it around a side or part way through, and its uniform density. Just figure out what your perpendicular distance is between the axis through the center of mass and the axis through your location of choice. Doesn't even have to be on the body. And multiply by the mass of the whole body. And remember to square that distance. So you can do a quick units check. They should be in length squared times mass. So if you keep your units with you, you won't forget that. That's a real easy mistake to make. So let's apply that to a slender rod. So we have a rod with a center of mass in the middle. Z sub c is right here in the middle. L over 2 in both directions, and we want to know what the moment of inertia of this body is around the end point. We're going to rotate around point A. We want to know the angular momentum, so we need to know z sub A, so we can calculate, we need to know I z sub A. And so we can look up in a handbook, maybe for a cylinder. We can take a look at our cylinder, where we just derived this for a cylinder that has some radial thickness here. Or we could say, well, it's a real slender rod, so R is much less than L, so that term kind of goes away. And if you looked up the moment of inertia about the center point of a slender rod that goes perpendicular to the rod axis, you would find this in a handbook. And you want to know the moment of inertia about a similar axis through the end. All we'd have to do is take the distance between A and C, perpendicular distance, which is L over 2 in this case, square it, get L squared over 4, and multiply by the mass of the whole rod again. So we have M times L over 2 squared, we get L over 4, add that to the moment of inertia about the center of mass, and we get M L squared over 3. Much bigger. Much bigger. So the contribution of having that greater mass further away from the rotation point, rotating around this point, is very, very significant. So your location around which you're considering your rotation is very, very important for these calculations. But this is a very handy trick to use the parallel axis formula to get the correct moment of inertia for the shape and the rotation axis you're considering. So you don't have to stop and do big integrals every time you want to calculate an angular moment of inertia or angular momentum of a rigid body. Okay. How about those products of inertia, those crossed terms? Literally, they're crossed because they include the mass distribution as a function of the distance from two different axes. And so they literally end up looking, there is some gauge of the asymmetry of the mass distribution. And we saw those in our expression for angular momentum of a rigid body that we defined. They ended up basically just falling out of our derivation for that expression about the angular momentum of a rigid body about any point inside itself. That ended up falling out, and I mentioned in the previous lecture that we typically don't end up needing these terms either because we have a body that is symmetric and they disappear, or in the case of the coverage of this class, we're restraining our discussions to planar motion where they would basically be inconsequential because we're not going to be applying any moments there. We would end up going out of plane. But just to give them a little bit of treatment, because there will be cases where you will be using them when you go to general motion. Two big characteristics to hold in mind. If you have a uniform density, and again, that's very important because if it's not, density is non-uniform, then all bets are off. Depending on the shape of the body, these two terms will disappear irrespective of the nature of motion if you have either axis symmetric axis symmetry around your z-axis, or if your xy plane, the plane we're considering our motion for, is itself a plane of symmetry, like a mirror plane across the part. So like bilateral symmetry down the middle of your nose for humans. We're bilaterally symmetric. So a plane that cuts us in half vertically, the sagittal plane, would be considered a plane of symmetry, just as an example. And of course, an axis symmetric type of part, a pipe, any kind of cylinder that is uniform all the way around. So in those cases, those products of inertia naturally disappear. You can calculate the integral and prove to yourself they do. And then even if you're not undergoing planar motion, those don't end up in your angular momentum expression. Even if you don't have a body that has this type of symmetry, we'll show that if we are undergoing planar motion, the moments that would produce angular momentum changes with time out of plane would be the ones that we would be dealing with for these two, and so we don't end up dealing with them even if they are non-zero. If you ever need to calculate these for any reason, for more general motion, for instance, if you're doing non-planar motion, just as a note, the version of the parallel axis theorem applies for both of these, except instead of just squaring the distance from a single axis, you just include the product of the distance in each direction to each of the two different axes of interest from your center of mass. So instead of a d squared, in this case we have a distance from the from an axis through the center of mass in the x direction and the z direction for I, x, z, and then y and z for y, z. Product of inertia. So very analogous, except we have two different distances to consider. Again, won't be using these in this class, but for more general motion and types of asymmetric parts, this will be important. And then you can remember, they will just be additional terms that you'll use to define your angular momentum, which will then, as we'll find out, can be related to your resultant moment with Euler's second law. And I am going to take a pause here and get to rigid body motion via Euler's second law in the next lecture, because it's a really big important topic that is basically the heart of rigid body planar motion kinematics. It's where we augment what we did with particle kinematics to include the rotation of that rigid body itself. So we're going to link up the angular momentum that we just wrote a lot of expressions for and for which we just reviewed how to calculate polar moment of inertia, which is a key part. Now we're going to put that together with an applied force or an applied moment resultant external forces. So this will be another Newton's second law analog to rigid bodies. So stay tuned for that.